Oh,
You
yeah.
can make a perfect.
Is that the one pigeons do better than humans on?
Is it?
There's one of those. Maybe it's Mastermind.
That would be interesting if people played Mastermind better in person, because Mastermind's a very logical game.
Yeah, yeah.
Thanks for isn't. I would understand the birds you play Thanks for. It's very spatial.
Yeah. There's lots of room for logic in the animal kingdom. All right, so other questions?
We talk about what's going to be on the midterm.
Yeah, we can talk about the midterm. I was going to do it tomorrow, but I'm doing it in the other class today, so.
Is it going to be like the other class where we just had to make code on paper?
There'll be some of that for sure.
Okay.
Will you print out a copy of all the Java docs?
Yeah, but I'm not going to give it to you.
Something very interesting thing to like put in the library or something. Here's a printed version of every, because they don't update them, do they? Java docs.
I think they do.
Well, they have to, yeah, because
I
some
guess
We have a new
some
version of
things
Java
do
that's
change,
outdated.
definitely.
I guess you would want to do that then.
So things to study and possible midterm topics. So review your programming assignments, okay? Make sure that everything you had to do in your programming assignments you're comfortable doing, okay? And that it's familiar to you. ODPs, we haven't done many ODPs lately, but look at those and look at your first 3 labs. I'm not going to hold you responsible for the GPIO stuff on the labs, okay? But you, in lab 3, right, you started using threads and did some multitasking, right? That's a good review of some of the basics in threads, extending a thread using the start method and so on and so forth. So review all of that stuff. Make sure you're comfortable with the whole idea of a class and an object, okay? High level view, class is the blueprint, object is the construction from that blueprint. How to define a class, right? So you want to be able to nail that syntax, right? You should know the keyword class, space, class name, curly bracket, definition, closing curly bracket, okay? If you've been relying on Eclipse or something else to write this for you, at least jot down on your notes somewhere, you know, a sample of the syntax for a class, for a public static void main, the basic things like that, because I want you to be able to do those. Fields and methods, right? So fields are like variables, and mostly we've talked about instance variables, so integer this, character that, right? Which are part of the class definition itself. Methods, which are functions, basically. And constructors, right? So things for creating an instance of an object. And also know about public and private, right? So private limits the scope to things within that class. Public opens it up to things in other classes as well. Be prepared to write code, modify code, analyze code. Okay, same as you've done on other exams. So I may give you some code and ask you to tell me things about it, answer questions about it. I may ask you to add some extra things to it or change things, or I might ask you to write code out of thin air. These will generally be, you know, construct a class with these characteristics, or write a method in this class that does such and such. And as usual, try to pay attention to what the question's asking and don't do more than it's asking for, right? If I ask you to write a class, you don't have to write a main method and show me using the main method and write all this other stuff and so on. On the other hand, if I say write a method that you know, deletes an entry from a linked list, make sure that's what it does. Don't spend your time putting in lots of print statements and debugs and things like that, right? Linked lists will definitely be on there. So defining a node, right? And usually our node is a separate class. So, and let me dig into this, because this was something I saw on PA2. So our linked list class Might have a data field. And I saw places where the next field was also a linked list class. And then maybe there was a linked list that was a sentinel. And then constructors and methods and so on and so forth. And this will work if you do it right, but it's not exactly quite right organizationally, because LL is a linked list, okay? It includes a sentinel node or some sort of handle to the first node. It includes methods for traversing and so on and so forth. This next field should more properly really be a node, right? The next field doesn't really need a sentinel or a handle to itself and so on and so forth. It should really be a linked list of nodes, right? So I would rather think of it like this. So your linked list is a node which contains a piece of data and contains a pointer to another one. Sorry, let me do this. So your linked list is a collection of nodes, right? Each node has a piece of data and a pointer to another node. And that node has a piece of data and a pointer to another node and so on. And so these LL nodes are these boxes. But the linked list itself is, logically, it's the collection of these things. Right? We're thinking of it primarily as a handle to the sentinel node or to the first node, which might be null if you don't have a sentinel. But saying that your linked list contains a piece of another linked list, you can make it work, but logically it's different from how we think of a linked list. Right? So it's best if you separate out the list itself from the nodes that make up the list. And when we do trees, that's going to be more important. So linked lists, what should you know? Defining nodes, right? How you get a list started, whether you have a sentinel or not. Adding nodes at the beginning, at the end, or in the right order along the way. Traversing the list, starting at the beginning and moving through every node until you get to the end. Searching for nodes, deleting nodes, and so on and so forth. Okay, not all of those were done in PA2, but we've done those things with linked lists in 222. So think about those and write some code if you want to practice. The scanner class, I want you to know how to construct it from system in, and how to construct it for a file by using the new file with an argument of a file name. Okay, so 2 ways to construct a scanner, and then next line, next int, and so on, along with has next line, has next int. So that whole idea of an iterator, right? Check to see if there's anything more, and if there is, get the next thing and iterate. All right, strings are another class that I want you to know some of the details with. So length, character at, 2 uppercase, 2 lowercase, substring, compare to, and equals. You should know those methods. Okay, there's a zillion other methods, and you can look them up in the real world. But these I definitely want you to be able to work with on an exam. And the equals method, you should understand why that is different from just using 2 equals signs. Okay, saying S1 equals S2 tells you if they're the same object. Okay, S1 dot equals parentheses S2 tells you if those two strings are comprised of the same characters. So that's what we usually mean when we say, are these strings equal? We really want to use the equals method. All right, you should know the toString method. Right? ToString is a method that's inherited from the object class or some other extension. And so every object that we create, every class we define, there's a toString that's built in. But if we write our own version of toString, then when we try to concatenate an object to a string, it'll call that object's toString method. Get a string back from the result and concatenate that instead. And so we use it to allow you to do things like pretty print an object, be it a rectangle or a vector or whatever else. So you should know the signature for toString, right? It's public, it returns a string, it takes no arguments, and it's called toString. So you should know what a signature is, right? Signature is the list of variable types for the arguments. Okay, which also implies the number of arguments that you're passing to it and the name of the method itself. So those things together give you the signature. Two methods with the same name but different types of arguments, totally different methods. Right? And when you call a method, the system looks at what types of variables you're passing to it and it figures out which method to invoke based on that. You should know that. You should know how to use try-catch blocks. Again, jot down that syntax if you're not used to writing it, because you can write clickety-clips and say surround with try-catch. But make sure you know try, curly bracket, list of statements. And then catch, and more stuff. And in this catch block, it takes something that looks like an argument, and it specifies what type of exception you're trying to catch here. So the most general case, and the only one I'm going to ask you to know for now, is just exception. And typically this is called E, but it's just a variable name. And if something goes wrong in the try block and it throws an exception, or something that extends an exception like IO exception, it will jump down to this catch block, and E will be set to whatever the exception was that generated the jump here. And then you can use that to diagnose why you're in here and so on. Print messages, whatever. So be comfortable with that syntax. Know how to work with arrays. So with these built-in types like integer, we can get away with that. But for these non-primitive types for actual classes, we can say something like rect. Right, which makes an array of rectangles. And then you can do this, which actually constructs an array of 10 rectangles, but those rectangles themselves, in some sense, don't exist. If we want to use them, we have to say something like x0 equals new rect, and construct it in the usual way. Be comfortable with static versus instance methods and fields. right, so these are instance variables. They belong to each instance of R, but if you use the keyword static, then that variable belongs to the class itself, and we can access it with the name of the class. Right, and this one you've got a single copy of these instance fields. You get one for each object of this type. And the same thing happens for methods. So if you say static area, static integer area, whatever, we can say rect dot area, and it's referring to that piece of code. And we don't actually need an instance of a rectangle to be able to run that code. So static versus instance, this keyword, so this refers to the object in which the keyword this is being used. And we use it sometimes in these mutators where we're trying to pass in the value of some instance variable and we want to use the same name in the argument list. But we use it more when we do class extensions. So if you say class superrect extends rect. So we're making a new class of rectangles called superrectangle, and when we say extends rect, it's got all the methods and all the fields from the rectangle class. But we can also write our own. So suppose we had an integer area method. We can make our own area method in here. And now if I have a superrect and I say the name of that object dot area, it's going to run this code. And anything in this class definition that uses the method area, it's going to use this code, right? But if I want to get back to the area method that was in the base class, the super class that I extended, I can say this, sorry, I can say super dot area, right? And that gets me up to the super class's area. If I were to say this dot area, that's just this one right here. So this and super let you talk about yourself or let you talk about the class that you extended, basically. All right, and for midterm, I will not ask you about swing, window builder, or the graphic class, or the paint method, because that's PA3, but that will be on the final. So not too much stuff. So questions about that?
What about the arrays? Like, this is basic arrays, difference between array and array.
Yeah, the idea that when you say suddenly blanking whether the bracket goes before or after the X. I think it goes here. When you do this, you construct an array X, okay? But if I try to do X bracket 0 dot area, I'm going to get a null pointer exception, right? And that's the only thing that would make sense, because how big is the area, how big is rectangle X bracket 0? There's nothing that's been done to give it dimensions, right? We haven't constructed it. So this is really sort of building up the array. In a sense, it's making this container with 10 spots in it, each of which can hold a rectangle. But right now, these are null. right? So when you say x bracket I equals new rect, right, that actually constructs a rectangle and puts it into that spot in the container. So with arrays, you kind of have this two-part construction you have to do. First you have to construct the array, then you have to construct the things that are going in that array, and then you can use those things.
But I mean, that would be the same if you were using like integers or stuff like that. You'd get weird values if you didn't. initialize
I
each
think it
one.
initializes to 0, or it'll give you like an compile error. But it's the same as in C, where you might say something like this. Right? And this says X is an array of struct rectangles, right? And then we could say X equals malloc 10 times size of struct rectangle. So now X is a space that's big enough to hold 10 rectangles, right? But if I were to ask for X bracket 0, it's not a rectangle. All I've done is set aside storage area for 10 rectangles. So I would still need to do this. I don't need to do that. But I need to populate X bracket 0, right, with the actual data of the rectangle.
Because wouldn't the first one?
Yeah, the first one will set aside enough.
Well, yeah, but I was thinking, wouldn't you set aside just the 10 pointers? Or are you making an array?
Right.
There you go.
Yeah.
And then the one below.
And then we go ahead and we malloc. Right, so X is a set of pointers to rectangles. And then this is the actual rectangles.
So when you're making in C, when you make an array of stuff like that, does it make, does it actually put the rectangles next to each other, or does it really do an array of pointers to rectangles?
If you say like this, you mean?
Yes, if you do that.
That's going to put them side by side in memory,
Okay.
right? And it's the size of this rectangle that's going to be the jump from one to the next. All right, so that's all. Do all that and you're good to go. So midterm is Wednesday, 50 minutes. I think it says 4 pages of notes, is that true?
Double-sided, right? 4 pages, double-sided.
Dude, you could put 4 pictures of notes.
If you write really small, you can like fit the Java doc. 4 pages of double-sided notes, look at that. Talk about a page budget. Yeah, that should be more than you need, right? Seriously, you should be writing down things to jog your memory or syntax you can never quite remember, or, you know, basic examples that'll help you stay on track with something. All right, well, let's talk about trees. In PA4, you're going to be back to working with trees. So this is a good time to pick up on some 222 topics. So I want to talk about trees and balancing trees. And remember, the idea of a linked list was that we wanted an array that we could insert things in the middle of efficiently, or delete things from the middle of efficiently, without having to move everything around in memory. So instead of assuming that the next element is at the next location in memory, we put in these explicit pointers So each piece of data tells you where the next thing is in the list, and now if we want to insert, we just have it point somewhere different. And we've broken this connection between successive elements in your array and successive locations in memory. So the list gives us better insert and removal time, but then search time can be an issue because you start at the beginning and you just kind of go through all your nodes. And even if your data is sorted, there's no way to play high-low on a plain old linked list. You need some way to access the middle of the list, and then you need some way to access the middle of the two sublists on each side, and the middle of the sublists on each side of that, and so on. And so we add these additional pointers that take us from the middle to these subtrees, sublists on the side, and that becomes a binary search tree. So each node has 2 pointers, one to the left and one to the right, and it's basically a list that's been augmented with this extra stuff. And so that works well in general. All right, so there's 7 things in your tree, and we can do a search for an item with at most 3 operations. Right, compare it to the root, and then compare it to the root of either the left or right subtree, compare to the root of one of those subtrees, and we're going to run out of nodes. If we don't find it, we know it's not in our tree. And if we do find it, we might find it after 1, 2, or 3 operations. And in general, this is order log n. Right, so it's the height of the tree, and if you have n nodes, the height's roughly log base 2 of n, because your tree doubles in width at each level. But the downside is when you build your tree, you might end up with something like this, and this is the same set of information as the first tree, and it's still a binary search tree. It still has this property of things to the left are smaller than the root, things to the right are bigger, but our search time is order n. And the reason why we've gone from log n to n is because it's just not very tree-like, right? It would look better if some of this stuff were over here on the left, and we've got, you know, all this potential space that we're not taking advantage of. And if we could fill that stuff in, then this will become shorter and wider, and we come back to this. So we have the concept of balance. And the punchline will be, the more balanced our tree is, the better the search time is going to be in general. And it can't always be perfectly balanced like this, because, for example, if you only had 6 numbers, this might be what your tree looks like, and we can't have another number down there in the lower right, because there's only 6 numbers in your tree. But this is still perfectly balanced. So we had this notion of how balanced a tree is. So T is balanced if the left and right subtrees are close to each other. And T left is balanced and T right is balanced. Or the edge case if T is null. But we want to be able to say more than just the tree's balanced or the tree's not balanced. We want to know what the balance looks like in general so that we can analyze when things are going out of balance. So we want something called a balance factor. So the balance factor is just going to be the difference in the height of the left and right subtrees of node n. And everything we're doing, we could define the balance factor to be the right tree's height minus the left tree's height, and every positive and negative will just switch roles for the next few days. So we're going to stick with this definition, height of the left tree minus the height of the right tree. And we'll be consistent with that. So what's the balance factor of this node 10? Why? What's the height of the left subtree?
0. There's not enough nodes.
So the left subtree is null, right?
Yeah.
So what's the height of a null tree?
Negative.
-1. So the left subtree is null, height of -1. Right subtree is null, height is -1. -1 minus -1 is 0. So you're absolutely correct, that has a balance factor of 0. And the same thing will happen on that 30 because its children are null. How about the 20? What's the left subtree?
0.
Yeah, it's just a node with a single root and no children. And the height of a tree with just a root is 0. Height of the right subtree is 0. 0 minus 0 is 0. So that has a balance factor of 0 also. Alright, now suppose we add another node down here to the left, 5. So any leaf node's always going to have a balance factor of 0. What about the 10? What's the balance factor here?
1.
That's 1. The left subtree of this is a node containing just a 5, and the height of a tree with just a root is 0. The right subtree is null, that's -1. So 0 minus -1 is 1. That's got a balance factor of 1. This has still got a balance factor of 0 because it's a leaf. And for the 20 now, the left subtree, what's the height of this tree?
1.
That's got a height of 1. What's the height of this tree with just a 30? That's 0. 1 minus 0 is 1. So if we look at balance factors, if every node has a balance factor of, I'm going to say 0, 1, or -1, then you should be balanced. So this is still a balanced tree. So let's add a 40. So this is a 0 because it's a leaf. What about the 30? Height of the left minus height of the right minus 1. And what about the 20? Well, what's the left subtree of 20?
It's 1.
It's the 10 and the 5, right? And this has a height of 1. And the right subtree is 30 and 40. What's the height of 30, 40?
It's -1. And it's also 1.
Height, not balance factor.
Oh.
1.
Yeah, so 1 minus 1, that's got a balance factor of 0. Right? Alright, so now let's put a 3 in here. So this is a 0, height of 1, height of 0, height of -1. That's a 1. Left subtree has a height of 1, right subtree has a height of -1. 1 minus 1, -1, that's 2. This hasn't changed, this hasn't changed. This, the left subtree, 3 nodes, that has a height of 2. 2 nodes, this has a height of 1. This has a balance factor of 1. But this is a problem. Okay, as soon as we see that 2, we know this tree is unbalanced. And the unbalance is happening somewhere around this node.
Isn't that where we have the whole if the left subtree is balanced?
Mm-hmm. Right, so the height of the left and right subtrees are close, right? The right subtree is balanced, but the left subtree is not balanced, right, from this point down. And there could be a whole bunch of structure up here. There could be a whole bunch of structure down here. But if we have a 2 at this node right here, we know that's where we're unbalanced. So when we're talking about AVL trees, okay, so these are balanced binary search trees. The whole game with AVL trees is to try to keep things balanced as often as possible. And if your tree is balanced, searching it's not going to change the balance, but inserting or deleting will potentially. So the idea is anytime that you insert or delete, you adjust your balance factors and you look to see if you're still balanced. And as soon as you find a balance factor of 2 or -2, you correct it. You do something to restore the balance. And if you've only got one node where you have an imbalance, it's pretty easy to fix. But if you insert 3 or 4 things and then go in and check your balance, you might find multiple nodes that are unbalanced, and now it's a whole different problem to restore balance. So we're going to try to keep it balanced after each insert or delete operation. So let's do some examples. All right, we've got a 20 and then we've got a 10. So I'll put my insertion order over here. We start off with a 20. And then we added a 10, so 10 went down to the left. And now let's insert a 5. And that's unbalanced. This has a factor of 0, this has a factor of 1, this has a factor of 2. So we can do what's called a right rotate. And in pictures, the idea is we kind of take this node and move it up to the root and take this 20 and bring it down. So if these are your 3 nodes, here, here, and here, we're taking this, which is lopsided, and we're going to change it into this. Okay, and it's kind of going to the right. It's going clockwise. So what does this mean? Take this middle node, put it up at the root, take the node that was the root, bring that down to the right. And so this is going to turn into this. And that's going to be balanced again. This kind of imbalance is called a left-left imbalance. So here's the node where the imbalance occurs, and it's unbalanced because we've got extra stuff on the left. And in that extra stuff on the left, there's also extra stuff on the left. Okay, so that's feels like it's really, really overweighted on the left side. Let me show you a different kind. So here's a 20, and then we put in a 10, and then we're going to put in a 15. And this is going to have a balance factor of 0, this is going to be -1, and this is going to be 2. So that's unbalanced also. But the feeling on this tree is a little different. It feels like we've got too much stuff to the left of this unbalanced point. We've got this whole structure over here, but in this structure we've got more stuff hanging off on the right. And so this is called a left-right imbalance. And we're going to correct this, but it's going to take 2 steps instead of 1. The first step is going to be to take this node that's 2 spots down from the imbalance and rotate that in place of its root. So we've got a structure like this. The first thing we're going to do is basically go like this. And that's going to put us in a left-left situation, and then we're going to go like this. So we're going to do this first rotation, which is going to turn us into 20, 15, 10. And then we're going to do this rotation, which will give us 15, 10, 20. And there's 2 things at play here, okay, and we're going to go through lots of examples tomorrow. There's 2 things at play here. One is trying to restore the balance, and the other is making sure you don't upset the search order. So over here, 10 comes before a 20. Over here, 10 comes before a 15, so our search order is 10, 15, 20. By moving this 15 up to the root, but then bringing 10 to its left, 10 will still come before 15, right? Whatever the root value is should come before the right child. So if we put the right child up at the root and drop the root down to the left, it still comes before the new root. And since all of those were to the left of this original root, they're still going to come before that. And then this other rotation where we rotate this up, 15 should come before the root 20. If we put 20 on the right child of 15, it's still going to come after 15, right? So the search order won't be perturbed by doing this. That's the essence of tree rotations for AVL trees, okay? The details are tricky because we need to be aware of the fact that all of these nodes might have other children and we have to know what to do with them. And in some cases, if we're moving a node to the right of 10, we might have a right child on 10 that has to get adopted somewhere in a way that preserves the search order. But these will restore your balance, and we'll see how to deal with children so that we keep the search order. So tomorrow we'll go through the general algorithm. Okay, and it'll basically be 2 cases, a left-left or a left-right, and then there's a symmetric pair for right-right or right-left. Right, and it's going to be exactly the same case, just everything's swapped. So we'll go through these cases, and this really is about turning yourself into this case, where you have a left-left. And then we'll probably spend some time on the board in groups, going through balancing some trees with this. And then Wednesday will be the midterm, and then Thursday we'll talk about red-black trees, which is a whole different approach to balancing. Okay, so we'll be doing trees all week. All right, so we'll start from there tomorrow.